All right. Welcome, everyone. We're going to get started. But first, I got, basic announcements. We got our quiz next Tuesday, written on the board here. We also have, I'm going to offer tutoring tomorrow, noon to 2 p.m. Just show up if you want some help. If you're having some problems or, understanding any of the concepts, I'll be in the room. You just walk in, and we'll work on whatever. If it's like large groups, we'll have everyone sort of helping each other. All right. Just going to kind of write that on here. Quiz 2. Tuesday. Tutoring. Okay. Otherwise, we were sort of entering a new chapter on energy. We've been talking about work. Work isn't quite what, yeah.
Just a quick question. So the quiz is going to be on the stuff on homework 3 and 4?
3 and 4, yes. Yeah. Like that being said, your quiz will probably, you'll need a calculator. All right. We started talking about energy and work and what it means for energy to flow from one thing to another. And I've had up just some basic, written on over top of it, basic sort of reminders of energy. Let me put them all up. Energy is constant throughout the universe. So at the very beginning of time, space, physicists are thinking it was what's called the Big Bang, when all of pretty much anything, all matter, all energy, all of the stars, all of the space between us was all compressed into one single sort of infinitesimal point. And then it gradually expanded, or I should say, expanded at an incredible rate until we had what we now know as the universe we live in. So that's just like, stars, matter, material, elements, all of the elements on the periodic table that went into forming stars, all of those stars creating, multiple arrays of planets, turning that into actual life. All energy is constant throughout the universe, wherever you go. Now, when we talk about things losing energy, they don't technically lose energy. Well, all they're doing is transferring their own energy to something else through whatever fashion that may be. So we're going to kind of talk about the types of energy. Energy determines how much work an object can do. So something has a lot of energy, that means that it can perform a large force over or a large distance or something of that sort. Some sort of combination of that. So we're going to be introduced to something called kinetic energy. From, just right off of just basic vocabulary, what do you think that means? It moves somehow. Kinetic means motion. So this is the energy of a moving thing. Or you can think of it as moving energy. So I'll put next to it moving energy. And all things that move have some kinetic energy. That's just a way of defining, this ball. You want to roll those? Let's roll this. This ball, or a car, or a bird flying through the air. Something that moves has a certain amount of kinetic energy until it is transferred to something else, and then it stops moving. So in this case, now it has 0 kinetic energy. Why did it stop? Well, first of all, we talked about friction earlier. We talked about, things that might force this to, forcing it the other way, slow down and stop. We'll get over what exactly those are in a minute, in a bit more detail. Let me write up the equation for kinetic energy. Your book, we will be kinetic energy is 1/2 mv squared. So Ke, that's kinetic energy, is the mass of whatever object you're looking at multiplied by the velocity squared. This also sort of takes into account, direction. We said earlier velocity was a vector, and it would kind of be a nightmare determining like left and right and up and down. So if we square velocity, it will always be positive, always be a positive value. So we have kinetic energy, how much energy of a moving object, a moving anything. And before then, we talked about work, things that force, it's a force over a distance. Work is force times displacement. But if you sort of break that sentence down, sorry, I tried to be you're fine. You break that sentence down, or so that thought, for work, I'm forcing something over a distance. I'm forcing something over a distance. Therefore, I'm making something move, right? So that was the equation of work up here. Let me add that up here at the top. Work was force times distance, right? Or I might have put like delta x for displacement. In fact, let me do that, just so it'd be more consistent. It's a force over a distance, and I'm making something move. We also have a way of describing the energy of a moving thing. So there should be a way to relate this force, me actually like pushing something, to how much energy this moving thing has. I could then maybe figure out, like, okay, this ball or this car currently has this much energy, and if I add so much more force, I can make it have this much energy. So we're going to make what's called the work energy theorem, where we have to sort of start out with some of those equations of motion from earlier. So this is just going to be a derivation. Your book does this. So if we had what was this one? This one was final and initial squared plus 2 a delta x. Okay. This is just an equation of motion. This is saying something's moving is an initial velocity and a final velocity. And there's an acceleration and change in position, whatever. Something's moving. We've had this before. Let's solve for, or let me do this. I'm going to subtract over squared delta x. And then, well, I'm trying to, show how this is equal to work. That equation up there at the top. So let's actually divide that 2 over to the other side as well. So if I divide the 2, it'll go under each of those v's. 1/2. Okay, now we're getting very close to something that looks kind of familiar. Kind of familiar, that kinetic energy equation I showed you guys earlier. But also the right-hand side over there kind of looks like work. So how do I take acceleration, turn it into a force? So that was Newton's second law, if you remember. F equals ma, and I could just, shift that around a bit. That becomes A equals F over m. So now if I put that down here for acceleration, I'm going to just flip to the other side. So I'll say F over m and then now we're almost there. We have a pesky m left underneath the force on the left-hand side. So let's multiply that over to the right. Then we'll see we have force times displacement is equal to 1/2. Let me actually rearrange this a bit. Not too much. Squared. Squared. So I've taken this just regular equation of motion as just something we learned in chapter 2, and I've related it to forces. Like I say, okay, now I can force something this amount, and I can make it turn into that speed. So this is just like a, we've had like this method we've been going through kinematic equations. So this is just like another way to get to the motion of an object. So maybe we're given a force instead of like an acceleration. Well, now we can use this. So we've related the work to kinetic energy. And then if you want me to go one more final step, this is basically me saying the final kinetic energy minus the initial kinetic energy. So how much does the kinetic energy change? That can determine, or that can show you how much work has been put into or out of the system. initial. All right, so this is sort of important in showing how we can go just from something, describing how something moves to seeing how much energy it has. And the energy says how far it can be forced in a certain direction. Let's do a little example. We have a hammer, a 2 kilogram hammer, swung off with an unknown velocity, and it strikes a nail. The hammer does 15 joules of work on the nail. So what we want to know is, what was the velocity of the hammer for this strike? So this can be like a reading on an actual staple gun could tell you the amount of force that the staples will come out. Or in this case, it's just your arm and a hammer. It'll give you a force, and you can sort of use this relationship between force and work and motion. So in this case, what would we do? Well, we know that, let's first write out what we know. Final. So we know that the amount of work that is done in the system is equal to the final kinetic energy minus the initial kinetic energy. Let me break it down to its full spread out form. Actually, I don't even need to do that for the left-hand side because we're given a value of work. We don't need to, we weren't given a force. We were given an energy. So we already have the value for that. So I'm going to leave it as W on the left-hand side. But on the right-hand side, final squared minus here's the thing. We don't know final or initial velocity, or do we? We want to find one of them at least. What can we assume the other one is? So we want to find when it's moving. The problem just says when it's moving. So we can assume it's a constant velocity. So hammer swing. Its final kinetic energy, right, 0, because it is striking the nail. It stops. And it delivers that much force, or that much work onto the nail. So the final velocity is 0. And that makes this whole first part of the equation, this whole first section 0 right here. So then it's just a matter of solving for the velocity, the initial velocity, v. And before I just put values in and go, divide and this and that, let's actually solve for v in just these terms. So that'll make it very easy at the very end. Otherwise, we might make a calculator mistake or something. So we have work is 1/2 mv naught squared. So we want to find v by itself. Multiply the 2 over. Multiply the 2 over. We got to divide the m over the left side. Then we're going to need to square root it, right? So what do we do? What do we do with that negative sign? It could be a matter of like just direction.
Question?
Yeah.
Where'd you get the 2 from again?
The 2.
2W?
All right. So not the bottom line, the line above it. So it's 1/2 on the right hand side.
Yes.
So I'm multiplying the 2 to the other side.
Okay.
As for that minus sign, we can see what the value is before before we judge if it's going to be a imaginary answer or something. So let's just find the value. Let's assume this is positive. I'm going to put it up here. 2, 15 joules over 2 kilograms. 2's cancel out. We get, I didn't do this beforehand, someone could do square root of 15. It's going to be about 3.87. Okay. 3.87 meters per second. Okay. So that's kind of a typical problem where we can take an amount of energy, an amount of work, and go using the work energy theorem and go kind of backwards and solve for just a very basic term like velocity. You could easily see how instead of an energy, instead of 15 joules, it could have been like 15 newtons, and that's a force. And so then we have to go a little bit deeper into this sort of relationship. So see, if it was a force, I would have then had to break this up like this. Does that kind of make sense? So we're sort of given new tools to play with for our sort of problem-solving skills. Yeah?
Can you explain again what happened to the negative?
The negative sign? I think it's just a matter of, I should have maybe phrased it like work done by the hammer, and I should have made it like negative 15 joules to begin with. So it's possibly just a mistake on my end. So, I don't know. Yeah. In this case, it also could have been like, something going to the right or something going to the left because of velocity. Right. Okay. So we have now we've done kind of an example of how the two are related. We could talk about conservative forces. So for there to be, some type of force that's labeled conservative, it has to only depend on the start and end point. So as I push your shopping cart, as I push this box across the table, as I lift the pendulum up, then let it go, or I finish my path, a conservative force only depends on how much energy it started with and how much energy it ended with. And if they're the same, then it's a conservative force. So the sort of middling path doesn't matter for a conservative force. Right, so a force is conservative when the path that's taken does not change the amount of energy that's transferred. And ideally, almost the perfect example of a conservative force is gravity. So, let me do it all over here. So, try to slow down and maybe describe a little, maybe in a different way, how a force can be conserved. Labeled as a conservative force. Say, if I have this ball and it's on the ground, it has a certain amount of energy. And now I'm going to pick the ball up off of the ground, and it doesn't matter where it goes. I could lift it up to here, and then I could put it back down on the ground. And now the ball has the same amount of energy as it did just that second ago. Does that kind of make sense? So conservative means it's the same. And gravity is a good example because, all of a sudden it's not, moving wildly just because I lifted it up and put it back down on the ground. So gravity is a almost perfect conservative force. I should also put in here along with springs. So we had that example of the ball sitting on the ground, and I lifted it up, and then I put it back down. But what if we had, I don't know, I'm going to make something really abstract, like we have a point here, called point A. We have a point over here called point B. And at point A, it has a certain amount of energy. It's a certain number, a certain, quantitative amount. And I want to travel from point A to point B. I can maybe take, a very long and, windy path like this. Maybe all the way over, and then end up at point B, where I will have this amount of energy, whatever point B is. That's going to be the same thing for a conservative force as if I went maybe just straight from A to B like that. Let's see. We did a crane example last time. So we kind of have another example of using this with gravity in just a minute. I thought I was going to do more on this slide. Never mind. Non-conservative forces. Those are the ones that don't necessarily help you out when you're moving. I should have brought that block out too. So one of the best examples of a non-conservative force is friction. So say I have this box right here, and I want to push it over there to the other side of the table. Well, I can push it directly there, or I can sort of push it that way, and then back this way, and then maybe I go back a little bit, and then forward, over, ends right here. I had to put a lot of energy into me making that very weird path. That's because this box had friction opposing it at every moment. So I had to put more energy into pushing it than if I went straight from this side of the table directly to this side. The total amount of force that I put in is different. So in this case, the path sort of, I say like it leaches some of the force from the motion. So the path does matter. In this case, let's see, I could draw a table. Same sort of example. I'm going to draw a table, and try your best. You do a 3D table. So if I have, if I have a box, and I want to push it from one side to the other side, I'm going to have to put, let's see, if I go from here to point A, point B, point C. So if I went sort of zigzag along the surface of this table, let me do it in like blue. Over here, then over here, then over here. You can see that's sort of a long path that it's traveling, and at every instance, friction is opposing the motion. And this will require more energy than if I just went straight to point C like that. So maybe I've repeated myself too much. Okay. Anyway, non-conservative forces take some of the energy out. Or I should say, they don't take the energy out. It's sort of bleeding into the table. Friction transfers that energy, me pushing it. It transfers the energy I'm delivering, into the box, and the box's bottom surface is transferring it onto the table and the other bottom surface of the box, creating heat. So friction is sort of sucking out some energy, turning it into heat as it rubs on the table. Because again, energy is never created or destroyed. Since we had gravity being that sort of perfect example of a conservative force, we can make sort of a very reliable statement about it. We could say that wherever an object is located, it's going to have some amount of gravitational potential energy. And since me having a ball down on the ground, I could raise it up, I could up and down, put it back on the ground. It's the same amount of energy. I could say, however an object is located, it will have a very specific amount of gravitational potential energy. So for like, any object ever, we usually say that as things get higher up off of the ground, they get more potential energy. We have this form we could write potential energy as so that's the mass of the object, the acceleration of gravity for wherever you're located. If you're on the moon, you'd use the moon's gravity. And however this object is displaced vertically. I should say, since we're going to have one more type of potential energy, I'm going to put potential energy of gravity. So this is gravitational potential energy. Or you could just have it as, G. All right. So what that means is that since gravity is, very predictable, we can have this potential energy form, and we can find an object's potential energy depending on how high up it's located. So that for this example, what do we have? We have a 2 kilogram book sitting at rest on a bookshelf. What is the potential energy, the gravitational potential energy, if it's placed 1.5 meters above the surface? Or, above the ground. So that's kind of like right here. 1.5 meters, kind of sort of shoulder height. Very simple. We're given a simple formula for this. So I write it as delta y. You also see it as like mgh. It's the same thing. So how high up is it off of the ground? For the first one, 2 kilograms times 9.8 meters per second squared. And that's a displacement. So typically we would call the ground 0. So 0 up. This case for that first one, let's see, I haven't done this one. 29.4 joules. Okay, so that's for the first one. And then we're going to take that same book, we're going to raise it up a little bit. So just by simply raising the height, I'm going to get a different potential energy. Let's do it again. All right. So we have two different potential energy values now. How does this make sense, though? So raising an object up higher, what I like to think of it, and you're going to hear just people saying potential. If you raise an object up higher, it will get a greater potential energy. So it's a certain value right here. It becomes more when I raise it up higher. And so I like to think of it as the potential of dropping, right? And if it does drop, if I drop it from right here, it's only going to be so fast, right? Because it only has a little bit of room. If I have it up higher, it has more room. It's going to sort of speed up more. So it has a bigger potential to turn into that greater speed, right? Yeah.
Why is gravity negative?
Gravity negative. In this sense, let's see, final and initial. Yeah, we can put it as negative. But what I'm going to do is I'm going to say final and initial. I'm going to sort of make the height flipped. So I'm going to say up here is 0, down there is negative. It's mainly because I just want a positive energy right now for this problem. And if I was going to be converting this to something else, then yeah, I'd need it to be negative. But in this case, no, it's fine. We'll leave it. Negative. These are negative energies. All right. Okay. Before I get into springs, so I have the pendulum up here, and I'm going to raise this ball up a certain height, and it has so much energy right now. It has so much potential energy, right? At this specific height. Then when it comes down, it's going to have a lower amount of energy, right? But things don't usually go from here and then they stop. Typically, if this was a perfect, if this room was vacuum sealed tight, there's no air in here, there's no friction. I wasn't even using this string, it's very heavy. If I was to bring this up and let it go, maybe you can see that it would go all the way over to this other side to the same height that I let it go at, right? That kind of makes sense at the moment? And it kind of does, right? So about this high, a little bit lower, but it's enough to maybe see. Now for this sort of demo, what I got is, this is called an interrupted pendulum. So now you see as I swing it, I'm going to swing it from like really high. So it'll sort of be stopped like that, right? What happens if I, if I do like this, it's, that very big swing on the other end. It's hard to see what's going on. But let's say I launch it from right here. Right here. How high up is it going to go on the other side? So, sort of showing that gravity is a conservative force, it will be the same on the other side. Even though the string is going to be shorter and has to do a whole different kind of arc. So, even though it has to change, and I show it at different positions. Here, that'll be good. Here, something. And you see, if I go higher than this sort of hole, that's where the analogy, this sort of demo breaks down, because then it sort of like loops back on itself. So I need to kind of go like right at the height. So that's showing that gravity is conserved and it doesn't depend on the path in between. So I have a sort of similar, bigger example of this on Tuesday. We get into springs now. Springs also exhibit a conservative force. So springs, they sort of follow their own force law. That's what we're looking at right now. So we haven't gone on and looked at springs when we were talking about forces. So we're going to look at Hooke's law. Hooke's law says how much force is required to stretch or compress a spring. So let's see. More specifically, Hooke's law equation looks like this. Kx. So we have the force. We know that already. What is this K though? This K value, that's the spring constant. And the X is just how far the spring is compressed or stretched. What is this spring constant? So I have this spring right here. Let me go get one more. never mind. So we have a spring, and you guys have probably played with like a slinky or something like that. It's like very like loose. How would I describe it? That's a very small spring constant. This one has a very, or I should say, much higher than a slinky. There are also springs in there's springs in your car, springs in your truck that hold the suspension sort of steady. Those are incredibly much more than this, or or like a slinky. So those sort of stay expanded, and it takes a lot of force for those to compress in your car. They keep your wheels sort of stable. So if we have two examples of stretching a spring or compressing a spring, let's see.
Why do you even need this?
No, that's fine. So it takes a certain amount to stretch or compress the spring. Now, this is sort of a bad example spring because I can't really compress it. It's physically all the way compressed. And this is its natural equilibrium state. That's not the case for all springs. Some springs might naturally rest, like those ones in the middle. Those ones can be compressed or stretched. And it's just which direction are they being altered. So here we have on the right, we have this sort of displacement. And here, over here on the left, it's about that big. That's the displacement. And right at the sort of equilibrium position, that's where we would call 0, typically. That's where our origin for this type of problem is. All right, so we have a nice way of finding forces around springs. Since springs exhibit this same sort of behavior as gravity, I do want to go like this. So like pulling on a spring. So at this moment, there is no energy within the spring. So sort of at rest. It's at its equilibrium length. This is the same statement as I said before, except now with springs. Springs are very predictable. I can stretch a spring all the way out here and return it, and now it has the same amount of energy as it did to begin with. And it doesn't change, and so it's predictable. I can make a potential energy around this. This new potential energy for springs is just called elastic potential energy. And elastic potential energy is the same thing, PE. So now this is elastic. I'm going to say elastic. One half. Let me see. kx squared. I think there's a negative sign. Let me see. Right, anyway. So we have this. No, there's no elastic. There's no negative sign. So we have this way of finding potential energy in a spring. We're going to do this last example, and I think we might call it good. Let's see. So we have a toy spring with a spring constant that is given, 24 newtons per meter, and it's being compressed. So I'm taking that large spring and I'm compressing it. I want to know how much force does it take to compress a spring like this? At least by that much. So, springs, force, that's Hooke's law. So I can always draw a little picture. Zero. So it's being compressed. Sort of forcing it. This is almost too easy. 24 newtons per meter times however far we're compressing it. I believe that's like 9.6. Yes. Okay, so it takes 9.6 newtons to compress this spring. Okay, that can be valuable. We want to know exactly how much to compress a spring. For some big project, we need so much space, so we need to know all these little parts. Next up is the potential, elastic potential energy of a spring. Again, pretty straightforward. We have the values. There's no big manipulations of the problem. (24 newtons per meter). But now we have to square this displacement. That's the only tricky thing. (1.92). elastic. Here's the force. Let's see. I just want to see what this next one is. Okay. Yeah, I'll start here next time. So, quiz on Tuesday. Tomorrow, I am doing tutoring, noon to 2. It's in the room right over here. Walk in if you need some help.